So the next paper we have group-based robustness. Yeah.
Thanks for the introduction.
Didn't introduce you. It would be nice to have underlined your name. Who are you?
Where I'm?
Okay, Varane Lin, first author. So let's greet the speaker. Okay.
Am I good to start?
Yeah, go on.
Okay, cool. Hello everyone. My name is Varane Lin, and today is my great honor to introduce our new work, Group-Based Robustness, a generalized framework for customized robustness in real world. This is jointly by Carnegie Mellon University, Duke University, and Tel Aviv University. What is robustness? In this paper specifically, we're talking about robustness against evasion attacks. So, what are evasion attacks? In this slide, we show two inputs of the same machine learning model. As you can tell, it predicts both of them correctly. One of them is a turn right sign, and one of them is a 30 kph. Now, when the adversaries add the perturbation to the 30 kph sign, it looks like a noisy 30 kph to humans. And if we feed this input to the same machine learning model, the machine learning model will predict a different class than 30 kph. So this is evasion attack. At higher level, evasion attack are slight perturbation made to the input of machine learning models to make them misclassify. The perturb inputs are also known as adversary examples. Depends on the goals of the adversary. There are two types of evasion attacks previously defined. One of them is untargeted, where the adversaries aim to induce any misclassification. In the example we've shown, the attackers only aim to induce a misclassification that's not 30 kph. There's the other type, which is targeted. The adversaries pick a specific target class in advance and only declare success when this target class is predicted. For example, they may pick turn right in advance and only declare success when this specific class is predicted. Now we have seen how do we define success of one adversarial example. How do we evaluate the model's robustness? The state-of-the-art way is to measure the fraction of inputs on which attacks succeed. Researchers iterate over a data set and try to generate adversarial examples for each of the inputs and see if they can do that. In the past decade, we have seen hundreds of papers competing on numbers according to these two metrics. At a higher level, prior to our paper, robustness is defined either targeted or untargeted. And robustness is measured on a per input instance basis, counting how many instances attacks failed on. And with this Plants vs. Zombie fans, if you're a video game fan, current robustness metrics do not always work. We'll see a few practical attack scenarios in the following slides. In the first scenario, the students are trying to steal unreleased answers. So there are 50 students and 10 instructors in the same class. The instructors include TAs and professors. And instructors can legally access unreleased answers, whereas the students cannot. Now, the students try to impersonate any instructor to steal the answers. They may use the eyeglasses text, which I show on the slides. So on the left, Liu wearing the eyeglasses might be misclassified as Mila on the right. And clearly, to humans, they are not the same identity. Now, we know that a correct classification is not a threat. And the question rises, is every misclassification always a threat? Here, we use certain mapping for illustration purpose. On the horizontal axis, these are the real identities, the ground truth labels. And on the vertical axis, these are the classified labels, the predicted labels. Each of the cell is a classification result from one class to the other. According to untargeted robustness, only when it's a correct classification, it is not a threat. So only when it's on the diagonal, it's not a threat. And all the other regions marked in red are all considered threats. So this is look like a diving flag, which you may see outside the conference room. And this is pretty much the area that we consider as threats. However, if we consider the rectangular area, thin rectangular area on the left, these are the ground truths as instructors. They are instructors, then they are classified as some identities. It might be instructors, it might be students. The instructors themselves already have legal access to the answers. So they have no motivation to impersonate others, and this area is less likely to be a threat. Students, after impersonating another student, can still get access, because all the students do not have legal access to the unreleased answers. And in the square region shown on the bottom right, these are students classified as students, maybe the same student, maybe different student. But this area are not threats, as the students do not get more access. If you look at the rectangular red region on the top right, this is what we consider a threat. Only students impersonating instructors is a threat. Only students impersonating instructors can give them access to these unreleased answers. Besides this scenario, we have a slight variant of this scenario where students try to steal unreleased answers, and there are still 50 students and 10 instructors. But instead of from the same class, they are now from different classes. The instructors can still legally access the unreleased answers, and the students cannot. Only students impersonating instructors is a threat as before. However, students may have different enough set of instructors they want to impersonate, registered for different classes, and they are less motivated to impersonate an instructor that does not teach them. So the threat mapping might look like these. As you can see, this is no longer a complete rectangular area. Again, students might impersonate different set of instructors, and only students impersonating the instructors teaching them is considered a threat. So here, we found that current robustness metric do not capture the risk in this students impersonating instructor scenario, as the student might not want to impersonate a specific instructor or any other identities. They want to impersonate any of the instructors. Now we're showing a different scenario, which is a bank burglary scenario. The bank has a vault, and the vault can be opened only if 3 staff members are present and agree. A group of burglars, at least 3 burglars, try to impersonate staff members. Again, they're using these eyeglasses attacks. For illustration purpose, we use another example. Here are 15 identities. 5 of them are burglars. 5 of them are staff members, and 5 of them are neither burglars or staff members. Again, on the horizontal axis, these are the real identities, ground truth labels. And on the vertical axis, we have these same 15 identities, 5 burglars, 5 staff members, 5 others. These are the predicted labels. Here I'm showing one possibility of success. Attackers win or declare success if all these 3 misclassifications showing the blue boxes happen simultaneously. It has to be happen simultaneously for the adversaries to declare success. Interestingly, the adversaries focus on this area marked in the pink region, which is they want to impersonate 3 different members, staff members. They want to find 3 blue boxes in this region. This is where the burglars are classified as staff members. However, there are more than one ways that they can declare succeed. I'm showing another one in the middle, and here's another one. And we have more. Specifically, attackers can still succeed if some burglars do not impersonate anyone. That being said, within this region bounded by the pink box, they do not have to find the blue box in every of the column. And even if some staff members are not impersonated, attackers can still succeed. That being said, for adversaries do not have to find a blue box in each of the rows. They only have to find 3 different impersonations. That's being said, they only need to find 3 block boxes on 3 different rows. And here, robustness cannot be evaluated on a per input instance basis. The robustness is measured on a set of inputs of the burglars, at least 3 of them. So they are measured on a set of at least 3 inputs at a time. And here, current robustness metrics do not capture the risk in this burglars impersonating theft scenario, as previous metrics only measure on a per input instance basis. As a recap, robustness prior to our paper is defined as either targeted or untargeted, and robustness is measured on a per input instance basis, counting how many instances attacks failed on. And in some practical scenarios, as we just shown, previous definition of robustness might not tell us how likely these attacks are to succeed, and we need new definition, new metrics to measure them. Motivated by this gap, our first contribution is that we have a new definition of robustness that better assess the risk. Enabled by these new definitions, we find faster attacks as our second contribution and better defenses as the third contribution, which I will show in more detail in the following slides. Our first contribution is a better assessment of risk. We formally define group-based robustness as a new metric that more accurately reflects true threats of the attacks. Specifically, we have a definition similar to a cryptographic game. And if we look at existing definitions of robustness, either targeted or untargeted robustness are special cases of our new definition, group-based robustness, when the cryptographic game has specific parameters. Here we show some empirical results. So we trained 100 instances. These models have the same architecture, same training code, and same training data. The only difference is their random initialization. They are random initialized with different random seeds, but with the same method. And here on the wider box on the right, we're showing our new metric. This is group-based robustness. On the left, we're showing 2 existing metrics, either targeted or untargeted robustness, showing similar box plots. All of these metrics have a scale from 0 to 1. And as you can tell, our wider box plot, the new metric, reveals much bigger variance between model instances within the same architecture. Our new metric suggests that models differ more than previous thought or what existing metrics suggests. We also found that group-based robustness is almost uncorrelated with existing metrics. We use Pearson correlation coefficient, compute the correlation coefficient of group-based robustness among the 100 models against existing metrics, which implies that none of existing metrics can substitute our new metric, group-based robustness, and first, believe stronger defenses might be weaker by the new metric, whereas our new metric better captures the true risks. That's our first contribution, and now I move to our second contribution, which is faster attacks. We found computationally cheaper ways to estimate group-based robustness using new attacks. Our attacks either find a similar number of attacks while being faster by a fraction of the size of T. T is the set of classes that might be impersonated. It could be instructors, it could be the staff members we've shown. Or, compared to another baseline, our attacks find many more attacks using the same amount of time. Due to time limits, I won't dive into more details of these attacks, but you're welcome to check out paper for more details. Now we move to the third contribution, which is better defenses. As we have shown, now we are better aware of the threat, which is a much smaller region showing on this mapping than previously thought. And in the real world, computation resources are always limited. So if we can devote the same amount of computation resources to avoid this much smaller region of threats, we may be able to train models to better avoid it. And empirically, we did it. So here on the horizontal axis, this is the number of iterations. As the training process progresses, it increases. And on the vertical axis, this is our group-based robustness, the metric that actually captures the threats. Showing blue is our method, a variant of adversarial training, and showing pink is the existing adversarial training method. Our method constantly achieves better performance than the baseline. We also measure the average accuracy. So this is benign accuracy, accuracy without the perturbation of the adversary. And our method also constantly achieves better performance. We also pay specific attention to a third metric, which is accuracy on targeted classes. So this would be accuracy on instructors or accuracy among the staff members. We don't want our model to never predict instructors, for example, although it will give them 100% group-based robustness and pretty good accuracy, benign accuracy, if there are very few instructors or staff members. So as you can see from this plot, our method also constantly achieved higher accuracy on targeted classes compared to the baseline. In summary, robustness is not always targeted or untargeted, and robustness sometimes cannot be measured on a per input instance basis. We need and not have better definitions of robustness. These new definitions enable us to have better assessment of risk, faster attacks, better defenses. You're welcome to scan this QR code to access the paper to find more details and find more cool things about our stuff. And thank you all for listening. I'm now happy to take any questions.
Thank you. I like your QR code.
Yeah, it's actually generated by ControlNet, and it's an image.
Hi, thanks for the very engaging talk. So like the example you gave for the students to steal the unreleased answer is definitely a valid case to demonstrate why we need a new metric like group-based robustness. But I feel like there may exist other scenarios where we may not need such a group-based robustness. For example, in the case of like a ML model in a medical context, where each misclassification could have a negative implication on its own without necessarily going to group-based robustness and stuff. So could you elaborate a little bit more on how this metric you're proposing is can be more generalized to different settings, such as the one I've just mentioned?
Yeah, sure. So as I mentioned, group-based robustness is a generalization or a framework for customized robustness, and existing metrics like untargeted or targeted robustness are special cases. So they are also counted as group-based robustness. So I won't say we always don't need targeted or untargeted robustness, but sometimes these metrics don't capture the actual risk. Does that answer your question? Or?
Hi, thank you for your talk. Are you aware of the paper Cost-Sensitive Robustness Against Adversary Examples by David Evans's group at University of Virginia?
I'm not.
So anyway, in that paper, they also define some non-uniform cost for adversary robustness. So basically, for the example of malware detection, we care more about malware to benign robustness compared to benign to malware, right? Because an attacker would always want to convert a malware to a benign sample, right, with adversary examples. So then, based on this definition, they create a cost matrix that captures this, which adversarial example type we care about, from which class to what class. So then they train a model using this cost matrix that reflects this cost, right? So then the model ends up being more robust from malware to benign compared to benign to malware. So one thing I didn't understand is how do you think this would relate to that? Maybe I didn't understand your work fully, but it sounded pretty similar to this, that we care about certain misclassifications more than others, from certain source classes to certain target classes. Could you explain?
Yeah, sure. So when you mentioned that paper, do they consider if I transfer benign to malware as threat or not a threat?
So malware to benign is a threat.
Yes,
but malware is less of a threat, so we don't care having robustness that much for that transition.
Yeah, I would say that's not a threat, right? Kind of, because you don't care if people transfer benign to malware, they're less motivated to do so. So I would say in that case, what they propose are a special case of our group-based robustness.
Oh, they don't even use malware detection. That's just an example I'm giving. They use other applications to evaluate. But I mean, the idea is the same though. like for certain source classes to target classes, we want to make our model more robust because we care about those misclassifications more than other pairs.
Sure.
So, like, so malware detection is just a reasonable example in this case, but they evaluate on different applications. So, like, how does this relate to that? Like, what you're doing? Because it sounded pretty similar. Like, we care about student to instructor misclassification compared to instructor to student misclassification. So we train our model to be more robust to that.
Yeah,
right?
sure. So I would say they're a special case. So first, like when you classify malware, it's one at a time, right? It's not several malware at a time. So here, like as we showed on the slide, like our general framework also captures the need for like if we measure not on a per input instance basis. So that's like special cases when you have per input instance basis, and then a special cases where that's not either targeted or untargeted. For the time, due to time limits, I didn't dive too much into the definition, but I think there are a special case in our definition.
Yeah, I need to probably check it out. Thank you.
Okay, thank you. That was interesting discussion. I would suggest we take other questions offline because, yeah, we need to keep timing as well. Okay, let's thank the speaker and